Hi, this is a REPL demo of the ont-app IGraph protocol. It's part of the ont-app project, which is a set of Clojure libraries dedicated to ontology-driven development. This protocol defines an abstraction which expresses a collection of named relationships between named entities. It is inspired by and aligns to the RDF model, which expresses knowledge as a graph consisting of subject, predicate, object triples. However, there is no direct dependency on RDF. It's written in Clojure and Clojure script, so it targets both the JVM and the browser. The core logic defines the IGraph protocol along with some related protocols, methods, and functions. There is also a module in the same library that expresses an implementation or defines an implementation of the IGraph protocol called IGraph. We can make an instance of IGraph with makegraph, and it has this type. This is suitable as a lightweight, in-memory data structure that can be used for annotations and such. It satisfies the IGraph protocol. Every implementation of the IGraph protocol needs a mutability model. In this case, we are immutable. So it satisfies the IGraph immutable protocol. IGraph immutable defines add and subtract methods which make cheap copies of the original graph before returning the modified version of that graph. So we can add our first triple in the form of John is a person, expressed as a vector. Every implementation of IGraph needs to, at least theoretically, be able to render its contents in a normal form, regardless of its underlying native representation. Normal form is a map to a set, subject to predicate to object. We can add more than one triple for a given subject using a vector, starting with the subject, followed by any number of predicate-object pairs. And here's our normal form now. We can provide triples for more than one subject by providing a vector of such vectors. So here we are introducing Mary and the stuff that she likes. And here's the normal form of that. We can also add normal form to an existing graph, which is harder to type in code, but makes it easy to dump the contents of one graph into another. And so here's the final contents of our GGraph. We can get the subjects of a graph, John and Mary. Clojure has this reduce KV function, which allows us to apply an aggregating function over the key value pairs in a map. Analogy to that, IGraph defines a reduce SPO, which applies an aggregating function to each triple in a graph. In this case, we just tallied the number of triples in our G. Functional invocation. The nice thing about Clojure, one of the nice things about Clojure, is that you can use its collection classes and invoke them as functions. So IGraph allows you to do that with graph implementations. So if we invoke G as a function without arguments, we get normal form. If we provide a single argument as the subject, in this case John, we get a description of John or Mary. If we provide two arguments, a subject and a predicate, in this case John likes, we get the set of things John likes, or the set of things that Mary is a. If we provide three arguments, we get a truthy response to the question of whether that triple is in the graph. So Mary is a person, but does not like liver. We can subtract from the graph using any of the formats that we use to add to it. Plus, we can provide a vector with two elements, in this case Mary likes, and remove the set of things that Mary likes, or a single element, in this case Mary, and remove the subject Mary. But because none of these values actually reset the value of our G-graph, and because G is immutable, we didn't actually change the contents of G. So one thing you want to do with a graph is query against its contents. This depends on the native representation underlying the IGraph protocol. In the case of IGraph, we use this very simple graph pattern query, a vector of triples, the triples describing a pattern within the graph using question marks to mark off variables, and it returns a set of binding maps to those variables. Other implementations, for example, SPARQL client would use SPARQL. Datomic and Datascript use Datalog, and we would query against them using Datalog. Another thing you want to do with graphs is perform set operations on them. Not always, but in cases like our IGraph graph where we have a modest size data structure, it makes sense to be able to perform set operations between graphs. So we implement the IGraph set protocol for G, which defines methods for union, intersection, and difference. To have another graph to interact with, let's read in a string of normal form from a file called types.eden. Has that content. You can use the read from file function to read the contents of types.eden into a new graph we will call types. Here's the contents of types. It's just kind of a toy ontology, taxonomy of types that relate to our G graph. Now we can take the union of G in our types graph, and here's the contents of that. You can see that now we have a little toy ontology that talks about John and Mary and the things that they like, and fit all of those things into a class hierarchy. We can take the intersection of our new GT graph and G and get G. The difference of GT and types is also the same as G. Another thing that we want to do with graphs is traversal. Now, Clojure and other functional programming languages have this reduce idiom where we can apply an aggregating function over the contents of a collection and accumulate the aggregation over that. By analogy to that, in IGraph we have a traverse function which takes an invariant graph, uses a traversal function, an accumulator, and a queue, and at the end of the traversal we get the accumulated value. So as an example of that, we can apply a utility function called transitive closure to the ISA relation, and it will return a traversal function which matches 0 or more ISA links within the graph. So ISA star is a function, and it has this signature, which is the signature of a traversal function. A graph, a context map, an accumulator, and a queue are the inputs. The output is a possibly modified context, a possibly modified accumulator, and an almost certainly modified queue. So, one application of ISA star, starting with an empty accumulator, and that queue, one application is that, roll it over again, we get that. And roll it over a third time, we get that. So we can see that our accumulator now has 3 things in it, and our queue has been manipulated at each step. Notice that we're not making any use of the context map. So when we apply a traversal function within the traverse function to our graph that we've called GT, we have an empty accumulator and the same queue. It will reiteratively call the traversal function until the queue is empty and return all of the things that are linked through 0 or more ISA-links from anything in the queue. Wherever there is a function invocation that takes a p argument, we can provide a traversal function as that p argument. And in this case, we will get the set of all things that beer is. Or if we provide an additional argument, we can confirm that beer is a thing, but is not a person. We can also use the tcomp function to compose traversal functions. Here we have a traversal of a single likes link followed by 0 or more ISA links. And when we provide that as the p argument against Mary, we get all of the things that Mary likes combined with the classes of those things. Or we can provide an additional argument and confirm that Mary likes junk food. So we need to concern ourselves, since this is not an acyclic graph, with cycles in that graph. So here we have Mary liking John and John liking Mary. We want to avoid an infinite loop when we get the transitive closure over likes in this graph. It does that by using the context map to track the history of things that have been encountered previously in the queue and skipping those. There are a few more of these traversal function utilities. One is called maybe traverse link, which traverses 0 or 1 links. We can also call traverse or applied to any number of other traversal functions, and it will take the disjunction of all of those traverse functions. So here we have the set of things that Mary either ISA or likes. And you can write your own traversal functions as long as you use the same signature of those functions. You will often find yourself making use of the context map to do things like apply heuristics, reorder the queue, prune the queue, or cache values, or otherwise optimize your traversal algorithm. Some properties will reliably be of cardinality 1, which is to say that the number of entities in their object set will be a singleton. So in our graph, the ISA relation is a cardinality 1 relation. We have this unique function which will unpack that singleton set for us. Now Mary likes more than one thing, so if we apply unique to that, we will get an error. There is an optional second argument which we can provide to disambiguate anything that's not a singleton set. In this case, we will take just arbitrarily pick the first member of the set. We can flatten a description, which returns a map with all of the singleton sets flattened out. And there's an inverse for that called normalized flat description. We can also assert a unique value. In this case, Mary is 20. Now we can give her a birthday, 21. So this has been a whirlwind tour of the IGraph protocol. It's available here. There are implementations for SPARQL endpoints, Datascript, and Datomic. and there are others in the works. Thanks for watching.